Thank you very much, Brad. Hi all, thank you very much for joining my session today. It's about the graph-based approach for advanced analysis of building design model. A few words about myself. I'm a civil engineer by education. I hold PhD degree from Germany in IT application for engineering. I'm running and the founder and running the IFC web server, which is a data model for BIM model or building information model since 2011. And I'm working as BIM expert at Dubai municipality since almost 5 years. So what we are talking about today in this session is how to deal with the complexity of digital model of building to and convert them to an efficient graph database to be able to access information, including a lot of complex relationship, filter them, query them, convert them to another format, and generate report. So there are three main topics of today: why, the problem statement, and how we do this workflow. And I will end it with some demos. If we got time, I will do some live demos. The presentation will be 15 minutes, but I'm happy to stay more if there are some questions or if you would like to see the live demos. So I assume not all of you are engineers, so let me start with some overview about what is the digital design models and as a preparation for the problem statement. For any building, as engineer, we design these models, and nowadays the building information model or using digital method or design program to design the model is the current art of the state. So for any building, we will have different disciplines like architectural, structural, mechanical, electric, and plumbing models. And this model could be very large and very complex and include huge information. How we exchange this model? We can use a lot of software to design this model. And the only common open standard for exchanging this model between different software or to process the information in a standard and open way is the IFC standard, which comes from industry foundation classes, and it's the ISO 16739. So the building, maybe you can assume that it includes only like slabs, walls, columns, doors, windows, things what we know usually. But of course, it could include more than that, out of complex electric, air condition, piping, cables, lighting fixtures. So you can imagine how complex it's sometimes to deal with this digital model if we are going to do some advanced analysis about complex things which are related to the building topology or the connectivity between electric or piping or cables elements. So, or to link this digital model with external information like sensors or any other external information for many use cases. If we simplify things and start with something we all know, like a door. A door inside a digital model can be actually described by many aspects and information. For example, the properties like the class is IFC door, the name of that object, global ID, etc. And a geometry, which could be simple and complex. And in IFC standard, there are many ways to describe the geometries in using a lot of low-level geometry. So the complexity of geometry can go very deep. Any element inside the building have a location, which is local location or global location. It has material, etc. And the most important thing is that building element have relationship with other entities, like connectivity included in decomposes of assigned properties, assigned material. This is what we will come to in the next few slides. So things can be very complex. So the problem statement of this, that accessing and managing information of this digital building model is very complex task from the information management point of view, because the models can include a lot of information, so large information volume. It has a lot of complex relationship between these objects. And it has also, from the schema point of view, multi-hierarchical or multi-level hierarchical inheritance level. So according to the tools which we use or which are available on the market, So these approaches and solutions usually fail mostly in performing complex retrieval and analysis of relationship, as I said, taking in account connectivity, building topology, path finding for indoor mapping, for example. So the potential here to use a graph database to store this information and to manage this information to solve such a problem. So what the solution was, or what the proposal was, to convert this digital model in IFC format to a Neo4j database. So we developed a fully automated and complete conversion workflow, starting by uploading an IFC model to a cloud-based data model server, ifcwebserver.org. And then with one automated task, we can generate comma-separated values for all elements inside that model, and then using the schema or understanding the concept of the schema itself on the meta level to generate a cipher script, which will be imported to Neo4j to generate or import at first all element or entities inside the model, and then to bulk generate all relationship between these elements, including two kinds of relationship: strong relationship and relational direct relationship. I will come to this in the few slides later. If you are interested to know more about like academic workflow or the research, you can refer back to this paper which I published almost 8 years ago, which deal with this problem, where I put more example and more like academic description of the problem statement and the workflow. So basically, the workflow consists of two conversion. One conversion is we started with converting, first of all, the IFC schema to a meta graph. The IFC schema actually is an express model. I'm not sure if all of you are aware about this express modeling language. I will show a simple example in the next slide. And to convert then the IFC model itself to an IFC-based graph. So we are talking about two graph is at the end. One is the meta graph on the level of each schema, because IFC has different schemas, official schemas and ongoing development schema, and the IFC model. After getting these two kind of graph to the database, we can start by filtering and querying. One of the features for our workflow that it supports having or hosting multiple models inside the single graph database. And this is very practical because usually, as I explained at the beginning, a building could have or should have or will have a lot of disciplines model: architectural, structural, MAP, and in most cases, we would like to deal with these models as federated one model, or in some cases, the model itself, it will develop through the time. So we would like maybe to compare what happened in the model, what has been changed. So comparing version to version or combining different model. At the same time, as I explained, that the building element inside a digital model in IFC has these hierarchical levels for inheritance. So here we are implementing the multi-label function of Neo4j to allow each object to hold labels for all parent classes, and this will help us a lot when we do any queries or when we create the relationship. Instead of repeating the same command to create a certain relationship, we start with the parent where this relationship was first time introduced. I will show some example in the later slides. So to start about diving a little bit deep in the technology or in the details, we are dealing here with two types of ISO standard. The first one is the express schema, which is ISO 10303-11, which is a standard for generic data modeling language. So maybe some of you know such graph, and this is very simple. Like if we are going to describe the person as male and female, and then put some attribute that a male could be a father, a female could be a mother, and every person should have a name. So this should be or could be the description of this class and relationship between them. On the other hand, the physical format, the step physical format, which is also another standard to save the information of the express model in a text-based. And as you see here, this is a simple snippet of this simple IFC file. So we see here we will have a header section, and then we will have a data section. And in this data section, we will have 100,000 or 100 of lines according to the size of the model. And every line starts with the step ID or IFC ID, like the entity ID, then the class name, then a set of properties or attribute to that entity, and a lot of entities will refer to other entities. So it is like there's a lot of interlinking inside the IFC model, which make the parsing them or reading them without any processing or parsing very difficult for a human being. If we want to understand the complexity of the IFC schema, we can refer to the 3 official releases which are available nowadays, starting with the IFC 2x3 TC1, which was published in 2007 and still commonly used. It has almost 653 classes. From these 653 classes, we have almost 100 abstract class and about 550 non-abstract class, which can have instances. And if we look to the relationship number, we see we have almost 50 relationship, 94. If we look to the latest versions, we see IFC X43 ADD2. It has almost 876 class. Among them, 743 are non-abstract classes. And then we have almost 47 relationship, and 5 of them are abstract and others are non-abstract. Of course, somebody may be asked why we should have 700 class to describe a building, because at the end, not all of these classes are referring to the building element or equipment or something physical we see, but a lot of them are low-level classes to describe relationship, to describe the geometry, to describe the location, etc. You can refer to the Building Smart, the organization behind the developing of IFC standard, if you are interested to know more. Of course, the workflow that I'm presenting today can be applied to any other similar product model. Like in automobile, there are a lot of standards and a lot of tools to save and to work with the product for different kind of product using the same ISO standards. Now, if we look to a building and we would like to see, for example, an example of where the relationship are used, so we can imagine any project, construction project, that it will have a construction site. So we're starting with the IFC project. It will be re-aggregate with IFC site. The IFC site can have many buildings. A building can have many inside the building. We can have building and part building. And then a building can have building stories or floors, and etc. So here we'll see as an example of this IFC rail aggregate relationship. And similar to this relationship, we see on the right side also a sample of relationship classes. So these classes describe the decomposition, the association of material, etc., etc. So this is another example of this multi-instance leveling. And in IFC4, we have maximum 8 level of inheritance. So if we look to a building, we will see that a building actually is an aggregation of 7 or 6 inheritance levels, going back from the IFC building to spatial structure element, spatial element, product, object, definition, route, etc. And here we can see as an example, when we convert this IFC model to a graph database, that we are using the semantic or the meta information of this express schema to define the cipher command to create the bulk relationship between all spatial structural element with the element which are contained in this element. How we start our workflow? We start, as I said, by converting the entities to SFZ, to comma separated values, then import them using the load CSV with header. And then we generate automatically the cipher command to generate the relationship between the nodes which already created in the first step. And again, we are not generating the relationship between the nodes one by one or by instance, but we are using here the schema itself to generate these commands. So in this case, we are saving time and we are sure that the conversion is fully automated. This is another example how things are like arranged related to the relationship. For example, any IFC element, for example, can be related to an IFC opening. If a wall has an opening, so there are two relationships, IFC rail fill element and IFC rail void element, and this will impact at the end, or will generate at the end, for every element which has an opening inside it as a wall, for example, two relationship, fill voids, which is referring that this opening filling these sorry, maybe fill voids for the windows and doors, here there is a mistake, but at least has opening, that this IFC element as a wall, for example, has an opening. Again, here I'm giving example. If we go back to the express schema, for example, for a column, we will see how these different color like yellow and green and brown are reflecting our generated command to generate the relationship inside the IFC model. So this is basically the approach, and this is the steps to generate the model. Now, if we would like to do some live demos, I provide you with a username and password to log into the IFC web server, and I'm using this building sample model to do the demo. After logging to the IFC web server and uploading the IFC model inside the online viewer, you will notice this model has a filter tab where a user can in one click filter element by type, by material, by geometry type, or do an interactive quantity takeoff. And what is interesting here, the user can even either select predefined cipher queries or can write his own queries to filter element according to very complex relationship. This is, for example, coloring by property value. So here we can choose any attribute assigned to any building element and choose which element we are interested in. For example, here I'm looking for, see the room name with different colors. So in one click, I will get this. And in the background, of course, for such all queries, a graph database query is generated and sent to the database, and we see as end user the result on the screen. If you would like to see the graph database after generation in interactive mode, you can also go to this address. I'm using here the IP address of the IFC web server because I'm not using a secure connection, to the /IFC_graph, where you can explore these models and play with them, or have the feeling how this graph database look like at the end. Some more example about what we can do after we generated the graph database or the IFC model to graph database. We can, for example, now navigate through this model. So one of the interesting things for graph database is connectivity between elements. So inside IFC model, there are some relationship between a space like a room and a door, and the next space like a corridor in this example. And here we can see with a relatively simple cipher query that we can generate a kind of connectivity between these rooms, and this will lead us to be able, for example, to use the shortest path method algorithm or similar algorithm to find the path or the connectivity between two rooms. And this is, for example, very useful for fire fighting, to find the ingress path if a fire happened. Another example, as I mentioned, if we import two versions of the same model, and we assume that at least the IDs of the element are identical, or the tag attribute in this case is identical between elements which are not added or removed. So in a simple query, we can define or find out which element has been added or deleted for that model. Another example is, if you remember, I show you here that we can, for example, in one click filter element by material. Maybe it looked very simple for people who don't know the IFC schema, but actually in IFC schema, there are different ways to assign material to the element, because the element maybe consists totally of one element, or it has layers of element, or it has layers with information about that layers like thickness, etc. So we see here that when a user click on aluminium, for example, and he got directly the result on the online viewer, that in the background actually we are using a kind of 4 queries and join the result and taking in account all possibilities how a material can be connected or assigned to the object. So this is another example of using the graph database. So what is the potential for the future, or what can we do after converting the model? Here in my approach, I try to make mapping one-to-one. So we are converting the IFC model completely to the graph database, keeping all relationship object or objectivized relationship. And we can, of course, even import the low-level geometry information, which usually don't have at the moment a lot of use cases, because this geometry is parametric. They are not representing the geometry of the model. So from my point of view, I think in the future, or what we can do next, actually we can make a cleaning for the database and remove any duplicated information, like objectivized relationship can be deleted because we already created the relationship between the object. We can do a kind of database harmonization and optimization. If you don't want to keep, for example, the attribute assigned to the element as a relationship, we can convert them to attribute. We can in the future integrate the Neo4j database with a geometry engine and process this geometry and either store them or link them in the database. So maybe we can do a kind of special queries or visualization for the modified model. There is another, this is on the level of the database. On the level of use cases, actually, there are huge potential for using graph database for management of BIM model. The simple one is linking BIM model with external data model. All people talking about digital twin, all people talking about linking BIM model with sensors, with document, with cost, with the planning information like timing or construction schedules, etc. So this is one of the possible things to do. We can, of course, develop based on this graph database QA/QC validation and rule checking for building regulation easily and more efficient than using SQL or other method. We can also work, and some researchers are already working on editing the information inside the graph database and exporting them back as IFC model, which should be not that complex thanks to having the meta schema in the database. All people talking about AI, about RAG model, knowledge model. So I think also naturally the next step could be to integrate this graph database with AI application and RAG workflow, so the user can simply ask you questions and the database can generate the cipher queries or give answers directly, and maybe working on advanced conversion method. So this is basically the first part, or the presentation part. I will look to the question. If there's any question, I will be happy to answer them. If you would like to stay like few minutes, I can also do a live demo, but please express this on the chat. Thank you very much again for joining the session. I hope it was interesting for you. So I see a few questions. I have to move a little bit to be able to read them. Of course, from my experience, I recommend using IFC model, and this is what we are doing for my professional work at Dubai Municipality. The BIM mandate is based on IFC, and IFC, as I said, is the only common standard. Personally, I'm not aware about what you called it, a brick schema. I will look at, I will read about it later. Another question. Mr. Anjar, please contact me. I will try to support you regarding your question, how to convert different comma-separated values to a graph database. Okay. So if there's no further questions, if somebody is interested to do a live demo, I would be happy to show. Otherwise, we can close the session to let you free to move to another sessions. So I think I got some requests to show very short live demo. So for that, I already logged in using the account I provided you on the IFC web server. Here we will choose the same model which I explained. I will open it on the online viewer. And as we see here, we start by visualizing the different classes inside this model based on graph database. The next maybe to show how we can filter element by type or by materials. And if you wish, I can show you how the graph data, the cipher command look like. We can further try also to filter element by the geometry type, etc. Or what is more interesting, maybe to see how possible actually to filter the element based on the cipher query. So here the user is free to use any cipher query as long as this query is about filtering elements. So at the end of every query, we should have something like return collect ID dash, and then the element IDs which are expressed in IFC ID attribute. So this is an example for filtering, for example, different building floors, to filtering only walls, to filtering, for example, spaces. So as you see here, or filtering, for example, object based on the name. So if I click on an element and I choose the name for this element, like 211, I can simply here go and say, I would like to filter any element which has 211 in the name. Okay, we have it. If we say like 2 only, maybe we'll have more elements. So as we see here, so it is very efficient, it's very fast, it's very flexible. You can write here difficult queries when maybe I didn't have time to write queries about pathfinding or complex example on this test model. The last things maybe to show as example this filtering or visualization or color by property. So here, sorry, the attribute name in German, but I will try to search for example, the room name. So it should be Raumname. So if we look for room name, actually I can select all object or spaces or the same. So we see here, if I reset, we see here that I got, for example, here the possibility to filter by the room name, and this approach is generic for any attribute inside this model. So with this, I think I hope that I explained to you quickly how is the workflow, and that I showed you some example. I will look again to the questions panel. If there is no further question, we can then finish the session of today. So I see no further questions. So thank you again for listening. Hope it was interesting. And thank you, Brad, for being my moderator for today. Thank you very much. I'll go back to the backstage.